Well, good morning, everyone. My name is Chuck Deschamps, and it's my pleasure to welcome you to the 2022 Farmland Drainage and Environment Conference virtual webinars. Today, we'll be hearing from our speaker, Dr. Masaki Hayashi, who will be presenting on groundwater recharge. Before I get into our speaker, though, today, I'd like to take a moment to acknowledge the numerous treaties across Saskatchewan, including treaties 2, 4, 5, 6, 8, and 10. Saskatchewan is the ancestral home of the Plains Cree, Sato, Nakota, Dakota, Lakota, and the Denisovan people. Saskatchewan is also the traditional home of the Métis Nation, and I would like to acknowledge and thank the diverse Indigenous peoples whose footsteps have marked this land for centuries. As many of you know, the conference organizers, the Citizens Environmental Alliance, was created to address the issue of farmland drainage in Saskatchewan, and SIA has partnered with other like-minded organizations and stakeholders to bring you these series of webinars. The Farmland Drainage and Environment Conference was initiated as the result of the Farmland Drainage Roundtable Workshop in Saskatoon back in 2018, where a wide range of stakeholders with interests in different backgrounds, including farmers, environmentalists, Indigenous peoples, academia, local governments from throughout Saskatchewan came together. And the one main conclusion from that report was that there is a need for education and communication to change perceptions surrounding the issue. Just a few housekeeping notes before we get in. Your mics are muted. But we will be taking questions at the end, so feel free to type questions in the question box, or when we get into the question period, you can raise your hand and we'll unmute you and you can ask your questions directly. So on behalf of Ducks Unlimited Canada, who I'm representing today and a proud supporter of this particular webinar, it's with great pleasure that I introduce to you our first sessional speaker, Dr. Masaki Hayashi. He is professor at the Department of Geoscience at the University of Calgary. He received his BSc and MSc in Earth Sciences from Waseda University and Chiba University, respectively, in Japan. And his PhD is in Earth Sciences from the University of Waterloo in Canada. His main research interests are in the connection among groundwater, surface water, and atmospheric moisture in various environments, ranging from prairies to mountains. So with that, I will turn it over to Masaki, and the table is all yours.
Well, thank you very much, for the kind introduction, and then thank you everyone for attending my webinar in the morning. I guess it's 9 o'clock Calgary, so it's a little bit early here. So I'm going to talk about the groundwater recharge in the prairies, and it turns out a lot of that recharge occurs through topographic depression, such as the one. This is about 100 kilometers east of Calgary, and we have a study site there. And then I took this picture about a year ago. It's kind of hard to, no, 2 years ago. Hard to believe. This was the beginning of the COVID pandemic, and then I wasn't allowed to do any university research, so I just took my own car and then told them I'm just going to go for a walk in the farm. So that's how I took this picture. So there's about knee-high water in this pond, and it's sitting there because the soil underneath it is still frozen. And then about a week after this picture was taken, the soil thawed, and then all the water went into the ground and it became groundwater. So that's the story I'm going to tell you in the next half an hour or so. But just to put that in the greater context, so there is this pairing of groundwater recharge and discharge in the prairie hydrologic cycle. So recharge in the prairies typically occur in this farmlands. This happens to be canola field, but this could be a pasture. And then, so it's located a little bit higher up. And then there are some creeks flowing through, and then groundwater is recharged on that land and then discharges along this topographic low places. So this is West Nose Creek, just north of Calgary. So you see the creek just snaking around this valley. That looks very lush in vegetation because of the creek that's receiving groundwater discharge, and also groundwater discharge is providing moisture to this riparian vegetation. And by and large, in the prairies, our water wells, let's say the farm wells, household water supply wells, more or less, shallower than 300-400 feet or about 100 meters. So that's the vertical scale we're looking at here. And then because the scale is rather small, only about 100 meters, so the horizontal scale is also small, a few kilometers to a few tens of kilometers. So that's a scale of small watershed. So this is what we need to look at in terms of sustainable groundwater management. So recharge is a simple concept. So you get rain and snowmelt water. Some of that infiltrates into the soil, and some of that runs off to the side. And then the plant roots take up a lot of this snowmelt and rainwater by evapotranspiration. And then what's left is going down past the root zone and eventually reaches the water table. So that's groundwater recharge. So this recharge and discharge are connected. It's part of what we call a water balance. We're looking at the groundwater, so it's a groundwater balance in watersheds. So that is a foundation of sustainable water management in the prairies. So it's the schematic picture. So you got the creek and the water table here, and then there is a recharge of groundwater. So I, often in a conference like this, I'll make an analogy of water balance in the watersheds with the balance of your checking account in the bank. So you got the revenue, so that's recharge. And then there are some expenses, one of which is groundwater discharge to creek or to the creek side springs, or feeding riparian vegetation by moisture supply. And there is another expense, which is pumping. So some farms may have wells pumping groundwater. So the balance between revenue, which is recharge, and expense, discharge and pumping, determines the change in the storage of groundwater, or in the bank analogy. So balance in your checking account. So the water level may go up or down depending on the balance between revenue and expense. So over the long term, though, we're looking at maybe a decade or a couple of decades. So there is what we call equilibrium. So the revenue and expenses are balanced over long term, similar to your checking account. So there are some ups and downs by and large, though it stays at the same level. So that's the cash flow. So it's really important to understand that cash flow, or the groundwater throughput, input and output for the sustainable groundwater management in the prairies. So we've been looking at this water balance in small watersheds for last decade, couple of decades in the research watershed. So I'm just showing two examples. So one's called the Big Hill Creek and West Nose Creek. So if you like going to the mountains from Saskatchewan, you may have passed through this Big Hill Provincial Park. So that's this Big Hill Creek watershed. So it's by and large agricultural land use, whether it's a grass pasture for cattle grazing or the dryland crops. And then the area of these watersheds are rather small. And then a while ago, we put stream gauging stations so that we can look at this balance of watersheds. So West Nose Creek's been monitored by us for about 20 years. And then Big Hill Creek is a bit shorter, only about 10 years. So this is an example of flow in West Nose Creek. This is year 2011. It happened to be a wet year. So we got good snowmelt, runoff, and then there are a couple of storms. And then, so the creek flow goes up during the storm. This is me standing in the creek, measuring the stream flow. But most of the times, these are my students measuring the base flow in this creek. So it's very low flow, just a little trickle going through. But this base flow is almost 100% provided by the groundwater discharge. So it happens in many cases, it happens through springs. So we kind of have a naive notion that, well, groundwater is oozing out to these creeks everywhere, but that's not the case. You know, groundwater input to these creeks happen in discrete spots. So for example, this is the source of Big Hill Spring. So this spring provides about 50% of flow of the Big Hill Creek. And so the West Nose Creek has several dozens springs we spotted. This is one of the largest ones. So this spring alone provides about 20% of flow of the West Nose Creek. So these are important for the creek flow, therefore the aquatic environment associated with the creek. So it's important to monitor this groundwater balance. So just like you want to monitor your the balance in your checking account, I used to get this, you know, the bank report every month in the mail, but nowadays a lot of people do it online. But Alberta, we don't have a lot of monitoring wells operated by the government, so we need to mobilize citizens. So a while ago, I worked with Rocky View County. So county is like a RM in Saskatchewan. So this is a municipal unit for the rural Alberta. So we recruited the volunteers, mostly farmers and acreage owners, and asked them to measure water level in their wells using this simple device. So we have about 30 of them that are still active in the Rocky View County surrounding Calgary. So it's been quite useful. So this was originally for the Rocky View County only, but then last year, with the help from a Global Water Futures program at the University of Saskatchewan, so we updated the system. So now we can accept membership from other counties in Alberta, for that matter, other RMs in Saskatchewan. So last fall, we added 2 wells from Foothills County, which is right next door to Rocky View. So this is 2 watersheds I mentioned, Big Hill Creek watershed and West Nose Creek watershed. So I'll show you an example of well number 20, well number 39, the water levels in these 2 wells, and then well number 325, okay? So well 20 and well 39 first. So here is the water level. It's we call it the relative water well level. So it changes against average water level. So you have this annual ups and downs. So it's revenue by the groundwater recharge during the snowmelt and the summer rain period. But then there are some years that there was no recharge, so there was no snow melt, or maybe rain was not very much, so no recharge for several years. So the water level kind of went down. And then we had the good years in 2019 and 2020. And as you might have heard, we had a drought in southern Saskatchewan, southern Alberta last year, so there's no recharge last summer. So this is reflected in the base flow in West Nose Creek. So this is base flow. We use a millimeter per year as a unit. And then so this yellow shaded area zone is this record here. So you see that base flow went up during the period of good recharge in 2011 to 2014 and came down, and then went up again in the last couple of years. And then 2021, it was a drought, so the base flow came down. And then this is the water level in that well 325, located in the West Nose Creek watershed. So you see the strong correlation between the creek discharge and the water level in the monitoring well. And the average discharge, the base flow in the West Nose Creek during this 20-year period was about 17 millimeter per year. So this kind of gives you an idea of that, the cash flow or the recharge, discharge going through the system. So about 10 to 20 millimeter per year. That's not a very large number, but it's a sizable number of. So, okay, let me just switch the gear and start talking about groundwater recharge. So we live in the northern prairie region, or the prairie pothole region. So it's this big green area, so spanning 3 provinces in Canada and then 4 or 5 states in the United States. So Calgary and Regina as a reference. So we live in a semi-arid climate. So annual precipitation is only about 300 to 500 millimeter per year, and the potential evaporation. So that's basically the meteorological demand for evaporation. So if there is water in the soil, the plants will use up this much, 700 to 800 millimeter per year. Okay, so this will be the amount of evapotranspiration from a well-irrigated field. So it exceeds precipitation by a large margin. So we're in a dry climate. And then we have a cold winter as well. So temperature sometimes goes down to -30. And in Calgary, we did have -35 in late December. And the soil freezes down to about 1 to 1.5 meters. So that's the climate. And then we live on the glaciated plain. So there were several glaciations. This was what the scientists call the last glacial maximum. So about 18,000 years ago, the land we live were under kilometers of ice, slab of ice. And then this glacier deposited glacial till. So most of that is clay rich. So here I can stick a knife in this drill core, and then the knife doesn't fall because it's so tight with clay. So it has a low permeability. And then also it left this undulating topography with lots and lots of depressions. So each depression formed this closed basin. So we call it the hydrologically closed because there's no surface water exiting these basins. So we have lots of this in the prairies. Now, so putting all those together, the semi-arid cold climate and then this depression-rich landscape. This is what happens in the spring. Hopefully this is going to happen again in about a month from now. So the snow melts over the frozen soil, and the frozen soil that's rich in clay, when it freezes, it becomes not very permeable. So it restricts the infiltration of snowmelt water. So a lot of snowmelt water runs off and find these low spots in the landscape, and they just form these snowmelt puddles or ponds. So this is what happens in the spring, and a lot of that actually infiltrates and becomes a groundwater recharge. So we did this monitoring study many years ago, almost 20 years ago, at a Saint-Denis research site near Saskatoon. That's on the Highway 5 towards Humboldt, about half an hour drive out east from Saskatoon. So here is this, typical puddle. Okay, so I'm making a note. This is not a wetland, so this will be seeded, and then crops will grow as soon as this water is gone in about a few weeks from the time this picture was taken. So we put a lot of instruments under this depression, and then monitored many things. So for example, the water level in the depression. So went up to about 30 centimeters, knee high. We were able to walk with rubber boots into this depression, and they disappeared by mid-April. And we measured the soil temperature at several different depths. And this graph, okay, so it's a complicated graph, but the vertical axis is depth. And the horizontal axis is the date, so from March to April. And the color indicates the temperature measured at a different depth. So the blue color with this thick line indicating 0, so this is frozen. So there is thawing from, soil started to thaw from the top in mid-March, and also started to thaw from the bottom. And then these two fronts coincided. So this is a complete thawing of the soil. And this is when the rapid decline of water in the depression started, because now the water can infiltrate through unfrozen soil. And then this is the water level in the monitoring wells outside and right in the middle of the depression. So this groundwater, the piezometer monitoring well was dry while the soil was frozen, and then infiltration started, then the water table started to rise. So this is a documentation of groundwater recharge focused under this depression. There are tens of thousands of them around the prairie landscape. So this is how we see depression-focused groundwater recharge. So there is a precipitation in the prairies. It's dry, only about this much. And then potential evapotranspiration, evaporation greatly exceeds precipitation. Therefore, on upland, all of snowmelt water and the rain is used up by crops, so very little groundwater recharge. But in depression, there is a transfer of additional water input, maybe knee-high or waist-high water sitting there. And then infiltration of that water can overcome evaporation demand during the summer, and that becomes groundwater recharge. But this depression occupies fairly small part of the landscape, maybe a few percent, 5%. Therefore, the landscape average recharge is only about 5 to 50 millimeter per year. So that's getting into our aquifers. So we wanted to learn more about this depression-focused recharge. So we set up this new project called the Groundwater Recharge in the Prairies, the GRIP project. So we conducted field-based process studies using a lot of instruments. And then based on this process studies, so we learned the new things. So we try to develop a model, mathematical models, computer models that can simulate groundwater recharge at a scale of individual depression. And then we wanted to scale up to regional scale. So we looked at remote sensing data and also used geostatistical upscaling. So looking at statistical distribution of depression size and depth, and in order to get the regional estimate of groundwater recharge. So these are our three main sites. So I'm going to talk about Spy Hill site, just northwest of Calgary. It's in the West Nose Creek watershed, and Triple G Farm are located about 100 kilometers east. So they kind of spans from Aspen Parkland ecoregion to the mixed grass prairie ecoregion. So this is an example of our field instrumentation. So evapotranspiration is measured by this sophisticated device. So it looks at the air in this little space and it measures actual motion of water vapor from the land into the sky. And this is soil moisture sensors measuring the moisture in the soil. And then we pull out groundwater monitoring wells and also collected sediment samples using these drill rigs. So first, the Spy Hill site. So we have been monitoring the precipitation. This blue bar indicates the monthly precipitation at the Spy Hill site. And then green bars are monthly actual evapotranspiration. This is the actual amount of vapor going from the land and plants to the sky. So it has similar pattern. So in the summer we get lots of rain, but then lots of evapotranspiration. So plants are using up a lot of that water. But the difference between precipitation and evapotranspiration indicates the amount of water getting into the root zone and going past the root zone. Okay, so there's no runoff at this study site because it's all totally closed. So over the years, that excess of precipitation over evapotranspiration accumulates a little bit every year. So on average, there's about 12 millimeter per year. So that's the average groundwater recharge at this site for last 15 or so years. So again, this indicates the cash flow through the system. So in the order of about 10 to 20 millimeter per year at this particular location. So we wanted to get more regional estimates using the field-based measurements. So we use this something called a chloride mass balance approach. So this diagram looks very complicated, but what it shows is, okay, when the rain and snow fall from the sky, those raindrops or snowflakes contains a tiny, tiny amount of chloride. So it's a very low concentration, but it accumulates over many hundreds or thousands of years. And then a lot of that rain and snowmelt water goes back into the sky, but then that's vapor going back into the sky. So the chloride is left in the ground. And there is this cycling of chloride between upland depression over many hundreds of years. And by the time it reaches the deep groundwater, So the chloride concentration in this recharging groundwater is quite a bit higher than the concentration in the snow and rain. So looking at this balance, we can estimate amount of groundwater recharge. So that's the principle of chloride mass balance. So equation is simple. Concentration in precipitation times amount of precipitation, let's say 500 millimeter per year, is equal to the concentration in groundwater recharge, which is quite a bit higher than the precipitation. And then this is the amount of recharge, let's say 10 millimeter per year or 50 millimeter per year. And then chloride concentration in precipitation in the prairies is well known, roughly on the order of 0.05 milligram per liter. It's a very small number. And then this is actual concentration of chloride in the soil and the groundwater, measured using those sediment cores obtained by drilling. So this is a triple G site about 100 kilometers east of Calgary. So under the depression, concentration is 1.2 milligram per liter, and under the upland, 86, quite a bit higher. And using this equation, so we can estimate the groundwater recharge under the depression to be about 14 millimeter per year and next to nothing for the upland. So this gives us a tool to look at the long-term groundwater recharge at a scale of individual depression catchment. So to upscale it to a regional scale, so we look at the chloride balance for individual depression and change the equation a little bit. So you get 1 over concentration in groundwater. And we average them for many, many depressions. So this is a mathematical symbol for averaging. But if we're averaging 1 over concentration, that is called a harmonic mean by scientists. Oh, sorry. In Alberta, we're lucky that there's a lot of oil and gas development. So when they do a new oil or gas wells, they have to look at the chemistry of groundwater in all the wells around. So we get this inventory of baseline groundwater chemistry, including chloride concentration. So we looked at this harmonic mean chloride concentration in regions in central and southern Alberta. So it looks like this. So concentration is lower in northwestern part, that's wetter and colder, and drier in the southeastern part. So concentration is higher. So from this, we estimated that in Aspen Parkland ecoregion, in this part of Alberta, the recharge is about 8 to 14 millimeter per year, and the mixed grassland ecoregion about 4 to 6 millimeter per year. So this gives us an idea of the groundwater recharge at a regional scale. And then we wanted to model this process. So we use this soil water balance approach. In this particular case, we use a model developed by PFRA back in 1960s called the versatile soil moisture budget model. Oh, so for those folks who are too young to know PFRA, so that is a kind of organization within the federal agriculture that looked at the prairie agriculture in particular. Unfortunately, it was dismantled 10 or 15 years ago. I can't remember when it was, but I was pretty sad when PFRA was dismantled. But anyways, so this is the model, VSMB model. So the rain and snow melt infiltrates into the soil, and then part of that actually runs off too. And then what's going into the soil, a lot of that is used up by the root uptake, whether by crops or the grass is growing in the pasture. And a little bit that escapes the root zone becomes deep drainage or groundwater recharge. So in Alberta, the provincial government used this VSMB model to map the estimate of soil moisture every 2 weeks, just so the farmers have an idea of the soil moisture condition to plan for the next growing season. So the red indicates not so good, right? Because we had a drought last year. So this is February 15th. So hopefully we'll get some more snow in the next month or two, and then we'll get a bit better moisture condition before seeding. So this model, we thought it was useful because it's been tested and proven in the prairies. So we took this model But this model was mainly intended for the growing season. It was very weak in the processes related to snow and frozen soil. So we added new modules for snow and frozen soil. So it modified BSMB model. And we also wanted to look at the interaction between the upland and depression. So in each landscape, there are hundreds of depressions of various sizes. And then we coupled them. So there is the runoff from upland to depression. So that's the coupling between upland depression. And then we looked at recharge from upland and depression, and then averaging them, taking into account the relative area of depression and its catchment, so we can get the landscape average recharge. So we wanted to validate the model, which is an important step when we do science. So model needs to be trustworthy. So we tested that at Spy Hill grassland site. So here is an example of soil moisture content. This is liquid water content. So the water that's still unfrozen. So there was a reasonable match between the model simulated water content that's in gray line and then observed water content, black dots. And we also looked at total runoff generation. So each year, so left column is the observed runoff. Blue is snowmelt runoff, red is the summer runoff, and then right column is the simulated. So there are reasonable match between the simulated and observed runoff. And particularly important was that there was no runoff year, such as 2010 and 2015. So that was replicated by the simulation as well. And another important factor we needed to consider is the fact that not all depressions have the same size and the same size of catchment. So here in this is a map of West Nose Creek watershed. There are thousands of depressions in this relatively small watershed, and this is a picture taken during the snowmelt peak in 2007. So the depressions filled with the snowmelt water shows up in black. So it turns out this size and density of depression matters greatly to groundwater recharge. So for example, this is a satellite image, and then you see many depressions, and then with respect to catchment areas. This one, for example, catchment area is this. We use alphabet AC, and depression area is AD. And we run the simulation of recharge using the same meteorological conditions and same soil, but changed the ratio of area of depression to area of catchment. So there's a sweet spot, about 5% area covered by depression. That's where you get the maximum recharge for the same soil and same meteorological condition. So when depression area is too small, not enough area to recharge. So you get small amount of recharge, but if the depression area is too large and there's not enough focusing of runoff into relatively small area. So that's how it works with depression focused recharge. So we wanted to get the estimate of recharge for the entire agricultural region of Alberta. So we got the help from Alberta Agriculture using their weather stations. There's 37 of them scattered across Alberta prairies. So each polygon represents the meteorological condition represented by each of these Alberta ag stations. And then we looked at this, density and size of depression. And then we found that it's dependent on superficial geology. What kind of landscape is there is dependent on what kind of moraine or till is covering the landscape. So combining these two information, here is the estimated recharge under the present climate for ungrazed grassland, because our data is based on the Spy Hill site, which is ungrazed grass. So there's no the grazing, cattle grazing going on. So under that condition, recharge is expected to be about 5 millimeter per year or less in southern Alberta, and quite a bit bigger in areas near Edmonton. So this is largely dictated by the meteorological condition. So another important factor that we did not consider in this simulation is land use, whether it's a crop or maybe the pastures are grazed instead of ungrazed. So I'll touch upon this a little bit later. But another thing we wanted to look at is the impact of climate change, because this seems to be on everybody's mind these days. So we got data from our colleagues at the University of Saskatchewan, group led by Yampin Lee. So they did this high resolution numerical weather model simulation for the present climate and the future climate for 2085 and 2100 using what they call RCP 8.5. So this is a do nothing scenario. So we just keep emitting the greenhouse gases, no mitigation at all. So they wanted to look at the extreme. So this is a worst case scenario. I think we'll probably do a little bit better than this in terms of keeping the temperature down. So there is about 4.5 degree increase of temperature. So red line is the air temperature average for this 15-year. A blue line is the present air temperature near Calgary. And then the bars are monthly precipitation. You see a sizable increase in precipitation. So the present climate is warmer, but also quite a bit wetter. So we fed this data to our groundwater recharge model. But remember, it's very important to have the snowmelt runoff for depression-focused groundwater recharge. So anything that affects the snowmelt will affect groundwater recharge. So we looked at the two things. First, snow accumulation under the present climate and the future climate. So this graph shows what we call the snow water equivalent. So it's the amount of snow, but expressed as amount of water for 2009 or 2094, and then subsequent 2 years. So you can clearly see that there's a lot more accumulation of snow under the present climate compared to the future climate, which sort of makes sense. And then another aspect is the soil freezing, because you need a frozen soil to generate runoff. So this graph again shows the depth on the vertical axis, and horizontal axis indicates time from November to October. So this graph shows 9-year average soil temperature. For example, March 2nd here. So it's the average soil temperature for March 2nd for 2007, 8, 9, 9 years. So it kind of averages out year-to-year variability. So it's cold. So the black line is a freezing point. So the soil is frozen down to about a meter and a half. And you can count on that every year, almost every year. And the future climate, okay, so you lose this, the consistently frozen zone. So March 2nd of, let's say 2092 might be frozen, but 2093 may be thawed. So you don't have this consistent frozen soil. So that means there will be less snowmelt runoff generation. This shows up in the recharge simulation. So the blue is the annual recharge simulated by our model for the spatial site, ungrazed grassland. In the future, the recharge drops, except for this year of 2015. Now, this happens to be the year in the future climate. There's a lot of rain. So the Calgary was hammered by very, very heavy storms. So that actually generated a big summer runoff and then caused the groundwater recharge. So the idea is that the future groundwater recharge may be reduced or maybe not, and then the timing will shift from winter to summer as well. So a few slides about land use. So it's well known that the grassland tend to generate less runoff compared to the annual crops under conventional cultivation. So we looked at that at the West Nose Creek Hydrological Observatory. So we have a few sites with ungrazed grass, a few sites with alfalfa. So this is a crop, but it's a perennial crop, and then annual crop. So there was a variability between different years, 2003 to 2019. Some years we got more runoff than other years. And then by and large, annual crop had the largest amount of snow melt and then ungrazed grass are the smallest amount. But we're a little bit suspicious of our data here because a lot of grasslands in Alberta are not ungrazed. A lot of them are actually cattle grazed. So we looked at that using a larger scale data, using satellite imagery and air photos. So this is part of West Nose Creek watershed. Yellow is annual crops, and then green is the grass pasture, mostly grazed by cattle. So here's an example of satellite image. And using this, we estimated amount of water sitting in ponds, and that gives us an estimated runoff. And then here is the grazed grass versus crop for 5 different years. So most years there was not a sizable, we call it the statistically significant difference between grazed grass and crop. So the crop agriculture, we have mostly adopted zero-till agriculture. So there's a less runoff generated by crop lands compared to, let's say, 20, 25 years ago under conventional tillage. And the grazed grass tends to generate a bit more runoff than ungrazed grass. So there's not a whole lot of difference. Now, okay, so final few slides. I'm going to talk about drainage effects because that's, major theme of this webinar series. So before that, I want to tell you about this important concept about the landscape setting and its effects on the interaction between groundwater and wetlands. So here are 3 wetlands located at a high position, middle position, and low position in the landscape. So the ground near the surface, maybe a top 3 or 4 meters, has a lot of fractures and macropores. So the permeability of this till is relatively high. So there's an active interaction of pond or wetland with riparian zone in the area surrounding wetlands, regardless of the positions in the landscape. Now, we have deeper groundwater flow, but this has to go through this tight, clay-rich, low permeability tills. So there is some flow, but it's very small, measured in a few millimeters per year. Okay. Now, but this small amount of flow is important for groundwater recharge of aquifers, such as this intra-till aquifer. These are the sand and gravel layers, maybe located 10, 15, 20 meters below the ground surface. A lot of cases, the farm wells tap into this intra-till aquifers. So that happens in this ponds located in the high position, and the low position groundwater flow is upward. So you see accumulation of salinity over thousands of years, and the water level tend to be stable in this wetlands in low position. So water table may be anchored by this low position wetlands. No matter what happens, in upland position, there's a stable anchor of the water table. So what's the effects of wetland drainage on groundwater recharge? So what recharges groundwater are these guys, these small depressions that have water only for a few weeks or a month. And then this pond, for example, will be seeded in early May, mid-May. And then these are wetlands, but these are not the place of groundwater discharge. They actually receive groundwater. So removing this type of wetlands have no effects on the groundwater recharge. So we wanted to look at some landscape with extensive drainage. So I talked to John Pomeroy's group at the University of Saskatchewan. They did a lot of study on Smith Creek. So that's quote unquote called extensively drained watershed. So I looked at satellite image on Google. Looks like, yes, they have drained a lot of wetlands. But I'm zooming into this section, upland, where a lot of these are located. So they either didn't touch these depressions, or they were not so effective at draining these depressions. So we're not really sure about the overall effects of this type of drainage. Okay, and then there's a line of evidence. So Garth Vanderkamp used to be at the Environment Canada in Saskatoon, now comfortably retired on near Victoria. So he sent me this graph a couple of weeks ago. So these are the water levels measured in intratill aquifers by Saskatchewan observation wells, going back to 70s. So presumably, landscape around observation wells have been drained to some extent, but none of them show any systematic decrease in groundwater level, indicating it seems that the groundwater recharge was not affected by whatever happens with the wetland drainage in these regions. And then there's an increase due to the last, a decade or so with very wet conditions. So these are the key messages for this seminar. So the groundwater recharge estimates are essential for sustainable groundwater management, particularly in the prairies. And the recharge in the prairies are relatively small, on the order of 5 to 50 millimeter per year. And they're by and large focused under those topographic depressions. So the climate change effects on groundwater recharge is not simple. So we will have a wetter climate, a whole lot more rain and snow, or maybe more rain in the future climate, but that may not result in the increase in groundwater recharge. And then finally, the drainage effects on groundwater recharge is inconclusive. We need to look at this a bit more carefully in order to make any scientifically convincing finding, and also the recommendation based on science. So these are the sponsors of our research over the last 20 or so years. And then there are many people involved in our research, and these are just a few of them who directly contributed to the results I presented today. Thank you very much, and I'll pass it over to you.
Well, thank you very much. That was very informative. We have a number of questions that people have typed into the question box. I don't see anyone with their hand up right at the moment. So if you would rather ask a question, by all means, just check the raise your hand box and we'll unmute you. So here's a question. Under climate change, could there be recharge during the winter with our milder winters with the sort of constant melt and freeze that we might expect under a climate change scenario?
Yeah, it's a very good question. I often think about it too, but I think, based on the relatively limited understanding we have, is that we still need to move that water, whether it's snowmelt or rain, to where it's focused. So if midwinter melt events can generate sufficient amount of runoff and then move it to the depressions, and then you do that a few times in the future climate. So this might, cause groundwater recharge. But so far, our simulations didn't see that happen. But it's important, remember, this is just a model. And we cannot fool ourselves by saying that, well, this is what model says, we believe it. I personally don't believe anything the model says until I see it with my own eyes.
Okay. Another question related to drainage is there a difference in the effects of drainage, whether it be tile drainage or surface drainage, say with a ditch? And sort of a second part of that, should drainage projects of these seasonal depressions, wetlands, be located near shallow groundwater wells?
Okay, so the first question, so I'm not sure how common the tile drainage is in Saskatchewan, Alberta, but I think it will probably have a stronger effect on groundwater recharge because you're basically taking groundwater below those depressions. So lowering the forcefully lowering the water table to wherever the tile is located. So that is my feeling or hunch. And then second question is, so whether these the drainage, should it be located near shallow wells? So what was the question
Yeah,
again?
so we're, you know, a lot of farm families, people that live in rural Saskatchewan, rely on wells for their water source.
Right.
And so the concern there is could there be effects that they might realize with their wells due to surface drainage or tile drainage?
Yeah, that's a good point. So I think it really depends on the depth of the well. So what we, Garth Vanderkamp and I have been discussing is that those deeper aquifers, whether it's intertell or, we have a lot of buried valley aquifers in Saskatchewan, and also some aquifers are bedrock aquifers. They tend to average over a larger part of the landscape, let's say a few miles. So in that case, draining a few depressions may not have visible effects on the wells, but it happens everywhere for miles and miles. You may start seeing some impacts.
Okay. Do farmers cropping or driving through these depressionals impact the rates of recharge or the amount of recharge? And then the second part to that, would infilling or filling in these depressions impact recharge?
So that's again a good question. So infilling the depression to a point where there's no ponding of water will basically remove that water from where it should be focused. So at a local scale, I think that it will affect the recharge process for that particular depression. But driving over, I do not think that will have much of impacts, because that water sitting in that depression will have a chance to infiltrate, even though the land surface is slightly disturbed by driving.
Thanks for that answer. I just see here that Chuck is frozen.
I know.
All right, let's see if we can pull up another question here. Okay, so is it possible to access whether land management practices can improve recharge potential? And is it possible to measure which depressions might be more important to recharge than others in an area? Hi, Chuck. We've just moved on to the next question here.
Yeah, go right ahead. I had a lost internet connection here.
Thanks.
Yeah, so again, that's, land use practice is something we have, thought about a lot. So, the 5 to 10 years ago, again, I often talk to Garth because he was in Saskatchewan at the time, and we've been working together for 25 years. And obviously, Garth is very knowledgeable about the groundwater in the prairies. But the idea was that, okay, so cultivation tends to increase runoff. So if we want to focus more water into these depressions, maybe, cultivation might enhance that recharge. But then we're finding that agricultures actually are changing, from year to year, decade to decade. I mean, the conventional tillage is not really that popular anymore. So conversion of, say, the grass pasture to cropland under zero tillage, I'm not sure how much of impacts that has. But the key is for individual farm operators to look at, a couple of key hydrological processes. One is snow trapping, and then the other one is how much of snowmelt is going into the depressions. I think the landowners will have a pretty good idea about what's happening. So if you see the depressions receiving a lot of water, and which is not one of those, big wetlands, so chances are those are probably worth retaining by land use management. Was there a second part of the question, or I can't remember?
Yeah, the second part to the question is it possible to measure which depressions might be more important to recharge, to recharge than others in an area?
Yeah, I think it also relates to the degree of focusing. Just in terms of simple-minded efficiency of recharge, the ones that have, much water, let's say the ones that you need the hip waders to walk in, and then the one that loses water within a month or so, maybe a month or two. So that will be the most efficient one in terms of groundwater recharge.
Okay. Another question here. It is likely that zero till may be causing more runoff. Sorry. I'm not quite understanding that question. Are there any other questions for Masaki, or if anyone wants to put their hand up?
Chuck, I do see someone has their hand up.
Okay. You know who that is?
Sorry, I guess I just lowered all hands. So if you did have your hand up, oh, Robert Halliday.
Bob, if you had a question, we can unmute you here. Go ahead, Bob.
Hi, Masaki. One question that went through my mind as you're making your presentation is that is there really enough data available in Saskatchewan to do the kind of detailed analyses you're doing in Alberta? I have a suspicion about the answer, but I'd like your opinion.
Oh, hey, nice to see you on, well, I don't see you now, but nice to hear your voice, Bob. Yeah, we used to run into each other in these the watershed conferences all the time. So yes, there is a bit of a limitation of weather data in Saskatchewan. So we're able to do what we did in Alberta because we got so many agricultural weather stations. So I think this was put up by the provincial government when times were good. We had a lot of money in the province, so someone had just a vision to put those weather stations. And also it was probably helped by the Alberta insurance, farm insurance agency as well. So that's one. But other than that, I think, so we need two things. One is a good weather data, spatial coverage, and then the other one is a good spatial coverage of superficial geology, which superficial geology, we have a good map in Saskatchewan. So in fact, we're actually moving into Saskatchewan now. I have a new student working on this, extending the coverage of groundwater recharge estimate from Alberta, first to maybe western and central Saskatchewan, and then all the way down to Yorkton. So that's what we want to do in the next year or so.
Okay, Jeff, I see you got your hand up. I'll unmute you. Go ahead, Jeff.
Yeah, I had a question regarding essentially the surface water and the groundwater and its relationship. I thought, what are the consequences to groundwater of increasing an effective drainage area in a watershed, say even 200%, like the effective drainage area of the growth starting at 30%? and then, you know, effective drainage area being at 90% as a result of drainage.
Yes, that's a very good question. Maybe I'll just bring up the slide, just show you some map shown in the beginning. Okay. So this is the map showing what we call the gross drainage area of the two creeks, Big Hill Creek and West Nose Creek, defined by our University of Calgary gauging stations. As you indicated, that the gross drainage area defined by the digital elevation map does not coincide with the effective drainage area, because a lot of these areas are not drained to West Nose Creek. But the groundwater is a different story, because groundwater does not need this surface drainage to get to the lowest point in the watershed. So we actually use the gross drainage area when we do the groundwater balance. So if in the future, for some reason, there will be less surface runoff and more groundwater recharge, so this will indeed, as you say, increase the effective drainage area of prairie watershed. But that's a very difficult to quantify, I think, but conceptually that notion is probably something we can support with the scientific data.
Okay, Clint, I saw you had your hand up. Did you have a question? You'll have to unmute yourself, Clint, if you want to talk.
I'm very familiar with the Big Hill Creek and West Nose Creek watersheds, having grown up in Calgary and got my degree from where you work in geology. But I live in southeast Saskatchewan now, and in our area, a large area of southeast Saskatchewan, our shallow bedrock is upper Cretaceous shale. So all of our water wells and that we use around here are shallow water wells in the glacial till level, like ridge moraine accumulations. So it's a little different than what you're looking at there, just because of the, you have a combination of all that foothills recharge and the snow melt in the, we don't have thrusts and folds and all of those kind of things to add to our aquifers. So for us, I would argue some of those longer term wetlands that are on the landscape for at least 3 months would be the ones that do more recharging than the smaller scattered ones, which the small scattered ones, those are gone here. Those ones are actively the ones that have been contoured out. So anyways, it is a the subsurface geology is pretty important as to what our soil horizon, our shallow aquifers are sitting on. And another recommendation would be to talk to the Aquanti guys that have built a model that integrates all of the surface geology and subsurface geology and data that's available, and have a pretty good computer model. It might be something worth working with, contacting those guys in your research. Anywho, thanks.
Yeah, that's a very good point. I couldn't agree with you more. So subsurface geology is very important. So this is what we typically have in Alberta, the region between Edmonton and Calgary. So we have this glacial till, which we're all familiar. And then, so oftentimes the farmers get the groundwater from this intertill aquifers. And then we have this shale and sandstone bedrock, and some wells are in the sandstone units, and some are from a buried channel. So, if you are looking at this relatively shallow aquifers in the till, this is a glacial deposits. And then, so what happens near the surface directly matters. But if you're taking water from, let's say, buried channel, or in some cases, sandstone units in the bedrock, so there is a bit of, I wouldn't call it disconnection, but not a direct connection between what we talked about, I talked about today, and whatever happens in these deeper aquifers. So a lot of cases recharge of these deeper aquifers. Garth and I started calling this replenishment of aquifers as opposed to recharge, is induced by pumping of these aquifers. So it is important to consider the subsurface geology. And in some cases, I agree that the bigger wetlands might actually become a recharge wetlands.
Yeah, because out here we don't have those deep sandstone aquifers. All we've got is the clay till type aquifers and the odd buried channel one. That's what we have, because once you get past that upper Cretaceous shale, now you're into saline type waters. That's it. But anyways, appreciate your research is awfully darn important, and we need to do a little more out here where the subsurface geology is different.
Thanks, Glenn. So 2 last questions here. One regarding zero-till. So producers that do zero-till typically do apply anhydrous fertilizers, which can tighten up the soil and reduce permeability. Have you seen any impact from that on groundwater recharge?
Well, I'm glad, yeah, you mentioned this. I was not familiar with that. This is something we should start looking at. So my short answer is no, but I mean, that's quite possible. We should really look at it too.
Okay. And last question we have. So in years where we have high snow cover, and depending on when the snow arrives and when the ground freezes, can have an impact, I think, on how less or how greater the ground is frozen. Are you seeing those kind of relationships, that sort of how our freeze up happens and how the thaw happens plays a major role?
Yeah, that's a good question too. So we have looked at that, but here, at least in the area around Calgary, so we haven't had a year where the soil didn't freeze past 1 meter on the upland. So from our research in other places, you need about ½ a meter or so of good frozen soil to restrict the infiltration. So as long as we have that 50 centimeter or 60 centimeters, you know, so it doesn't really matter whether it's frozen down to 1 meter or 1.5 meters. So under the present climate, so we're seeing consistently high snowmelt runoff as long as there's a snowpack there and melt rather quickly. But in the future climate, when you only got 20 centimeter of frozen soil, that could be a different story.
Okay, very interesting. Okay, I'm not seeing any more questions. Bob, I see you still have your hand up. Did you have a question or no?
I see Wendell Koning actually has their hand up.
Oh, okay. Go ahead, Wendell.
Yeah, hi, Masaki. Thank you. It's Wendell Koning from Calgary. Masaki, one question, slightly different, but how would gravel mining operations, open pit gravel mining operations, impact groundwater recharge?
Yeah, okay. Yes, yeah, gravel mining is on a lot of people's mind around here nowadays. So the mining itself, well, I guess a removal of till, and then so that will basically short circuit the snowmelt to the aquifer. So the area that has been mined, whether that's a quarter section or 1/8 of a section, so you will have a greatly enhanced groundwater recharge. So that's probably the direct effect we would see. But then there's also other issues like the quality issue, right? So you're not really protecting that quality with the thick layer of till. So you may actually get snowmelt water with a lot of stuff we don't want getting directly into gravel aquifer. Yeah, so that could be a bad news.
Okay, I'm not seeing any more questions. So I think that will be it for today. We'll maybe wrap it up now. I want to thank Masaki for his excellent presentation. And with that, I guess we'll bring things to a close here. If you haven't seen, we have 2 webinars left in the series, starting tomorrow and Friday at 10 o'clock, same time. The first one on Thursday will be Does Drainage Pay? And then the second one will be on an update from Jeff on farmland drainage and the environment. So by all means, if you haven't registered for those, do take them in. You can stay connected with the conferences and the information simply by following the Citizens Environmental Facebook page. As well, if you're interested in learning more about what started this conference and some of the background information about what the stakeholders thought in relation to farmland drainage, the information is there. Just follow the link. And I want to take a moment to thank our supporters for helping organize this conference, arranging speakers, and taking the time to line up the various speakers we've had. It's been a very interesting series, and I know everyone has been very pleased with how things have turned out. So on behalf of Ducks Unlimited and all the supporting partners, I want to thank Masaki for such an excellent presentation. And with that, I wish you all a very good day and enjoy the rest of the week. Thanks, and thanks for attending.
Thank you.